Welcome to the intersection of technology, cybersecurity, and society. Welcome to ITSP Magazine. Knowledge is power, now more than ever.
Hello, my name is Charlie Camarda. I was an astronaut on Space Shuttle Discovery's return to flight mission following the Columbia accident, STS-114. I will be your host today on Leading Edge Discovery podcast in conjunction with ITSP Magazine, where we will be talking with experts around the world on science, technology, engineering, and math, and in particular research. And our first series of episodes is concentrating on aerospace and research scientists at NASA and around the world. And in particular, we're going to be looking at critical problems. I call them epic challenges that we try to solve, like what causes these accidents, like Columbia. And so this is a tribute in many ways to the men and women who helped us return to flight safely and why their expertise was needed. And I'm very lucky to have a friend and colleague that I've known ever since I started working at NASA Langley. His name is Dr. Olaf Storaasli. He's a subject matter expert. He's a research engineer in the field of structural mechanics, computer science, high-speed computing, and parallel processing, and probably lots more things, Olaf. And I want to welcome you and thank you for agreeing to be a host on the podcast. And I like to begin the podcast with your story, your introduction as to how did you go down this path? How did you end up in research? And how did you end up in the field, that niche that made you that expert?
Well, thank you very much for letting me participate. And I've been following you for years, and I'm so proud of you and what you've done for NASA. And I remember when you were there and we were impressed with what you were doing at Langley as a researcher. And then you said you're going to be an astronaut. Why would you leave such a beautiful research career? Anyway,
we'll get into that.
Yeah, as far as I'm concerned, I had two mentors. My dad was a theologian, and they all expected me to go and be a minister or something. But my uncle, Dad's older brother, he went to MIT in electrical engineering, worked on the Manhattan Project, so he inspired me. And, one way he inspired me, we'd all get together in Minnesota at a lake cabin, and he would do all these fantastic things, just like magic, One day.
Wait. I have to just interrupt for 1 minute. You glossed over it. So he worked on the Manhattan Project.
Yes, he did. With Lawrence, who was the one that was a Nobel Prize winner. Lawrence was the theoretical guy and came up with the idea of the calutron. And Uncle Barr was in Milwaukee where they made them. And one day he said they got all this silver from Fort West Point, and he said, I'm responsible for all that. They had to put them together, and they eventually ended the war because of the.
So was he like at Los Alamos?
Oh, he was at Berkeley, and then he was at Oak Ridge, and wasn't at the detonation. From Oak Ridge standpoint, the detonation was what they did at Los Alamos, but
yeah,
the work and the money was at Oak Ridge. Anyway, he was a big inspiration. One way was, like I told you, magic. My dad said, we're going to go fishing. And Dad said, go and dig up some worms out by the outhouse. And Uncle Barr said, no, go to the garage and get two spikes. He put them in I brought them, he put them in the ground. He put up a toaster on one and put some wires. And then between the two, the worms started coming up. And he said, okay, collect the worms and you can go fishing.
I heard about this.
And the other one professionally that was a mentor was Ray Clough. And if you read about him, he's the one that really came up with the finite element technology. And he did it in Norway, of all places, on a sabbatical. He was a Berkeley professor. And he not only did the theory, but then he went and worked with Jim Toaster, who was a friend of mine at Boeing. And he'd go up to Boeing on summers and they got some of the early finite element codes, and then we were able to bring those ideas into Langley, which eventually developed into Nastran.
So Clough was really the father of finite element methods,
Yeah.
which for our viewers is a numerical method to solve partial differential equations.
Oh, yeah, and he had a vision for computers too, because he worked with Jim, and the computer technology was taking off at the same time the finite element theory could be implemented. So when I came to Langley, it was like the best of both worlds. I'd had some things related to finite element technology when I was working on my Ph.D. at NC State. And my advisor, Dr. Gurley, worked with Bob Fulton. He'd go up there summers and work with Bob Fulton. The summers he didn't work with Bob Fulton, he went out to Oak Ridge Labs. And those are the two places in my life I've been.
And Bob Fulton had been working at NASA Langley.
Yeah, and his brother was also a pilot that shuttled or carried the shuttles on the 747. I met him too. My feeling about research when I came to NC State, you know, that you could do different types of things, but I really liked to work with Ed Gurley because he had connections with NASA. He'd go there every summer. And so then when, you know, I kind of came into that and I was challenged. His thesis at Illinois in civil engineering was on thermoelasticity. So I went, by that time, the computers had developed to the point where you could actually solve the coupled equations of thermoelasticity. That was my thesis. So it was a natural thing to go into the research environment. Wow. I don't know. Do you want me to say more?
No. Okay, so 1970, which is very interesting. You started working at NASA in 1970.
Right.
I actually interned probably in the same building where you were. I was a junior at Brooklyn Polytech the summer between my junior and senior years, with the most amazing people in structural mechanics, all in this one building. You were there, Fulton.
Sid Dixon was too.
Sid Dixon, Jim Starnes,
Jim Starnes.
Ahmed Noor, Jim Robinson,
yes.
Carson Yates, the expert in aeroelasticity. Yeah, it was an amazing.
All the experimentalists were there, and it was a big lab, so we could get a firsthand experience. It was fantastic. 1229, a wonderful place to work.
And so then you start, and was one of the first things you did was that working on the finite element machine, which is
we did that later. The first thing I did was they had me go to different companies. The force method was used by McDonnell Douglas, and Boeing was using a displacement method. And they said, Olaf, we want to really move out and have our own code so that we can test the different things instead of having each company do their own finite element code. We wanted one. So try and find which is the best thing. So I went, McDonnell Douglas had a force method, was really good, but Boeing had displacement. So I wrote up and said, I really recommend the displacement method. And then they decided to have Nastran developed by the displacement method. But we had in-house codes that I worked on originally, one from Duke University that was pretty good, ELAS it was called. And so we tested out things, but then Nastran developed to the point where we got an early prototype that we could use on the Viking project. So my first thing was in Viking, working with that.
That's right.
Even though it was in 76, it was like 73 when we were doing all the analysis early on. So these projects, you know, take a long time.
And what a lot of our listeners don't know, when they think about Mars and they think about Mars landers, they think about the Jet Propulsion Lab.
Oh yeah, it was the Langley project.
Yeah.
They got the feeds coming down from JPL, and of course JPL had nice signs that they put up, and so the TV, everybody think it was JPL, but virtually everything was Langley.
The entire project was run out of Langley.
Yeah, actually,
small little research center.
Headquarters before he started it. It was his baby, and he came down to be our director because he was very personally involved with it. He even went to recruit people. He went to the Research Triangle, and when I was finishing my PhD, I went in to interview, and that was Ed Cordwright. He had a meeting down there, and he was trying to get people. And so I was the last one of the day he interviewed because I couldn't get on the list, and I just stayed there and interviewed. And then when he retired, he said, "Oh, Olaf, I remember when I interviewed that day down at NC State."
Wow, yeah, I remember. I remember Ed Cartwright. Of course, he was there. He was the first center director when I started at Langley, also. But NASA Langley ran that entire project,
Oh, yeah.
and you worked on the gas chromatograph mass spectrometer. They were having problems; it was leaking,
Yeah.
and you had to do some structural analysis. And I think you redesigned the whole box.
Yeah, that's true. But before we did that, they asked me to do the static, dynamic, and frequency response for the design of the lander. I did that and a little bit on the orbiter. And then later, the GCMS box was a problem. And so Jim Robinson and I were the structures guys, and Dick Snyder was in charge of us, that we redesigned the whole box, just went in from a, what do you say, a piece of paper and started over and did a finite element model. Because Litton Industries had a box that wasn't working. They delivered it and it leaked. You know, it has to be pressurized and has to work 9 months on the ground, 9 months before at the Cape, and 9 months in transit. Well, no, 9 on the Earth, 9 in transit, and 9 on the moon. But it actually on Mars. But it actually lasted, I think, almost 5 years, and another 3.5. So.
But this is interesting. So this is the first time finite elements is really being used commercially to design something. And so being a good engineer, you're validating that with some other analytical technique, right? And you're improving and you're constantly adding degrees of freedom to your finite element model to see if they match, and you're going through that whole process.
And we work with the experimentalists too that would try things, you know. That was a nice thing about 1229 and some of the others. You could talk to people that had firsthand experience.
Okay, so you also validated with experiments. So you go out in the laboratory and conduct some tests.
We designed the thing at Langley, Jim and I, and Tom Jones. He was from systems engineering. And so we designed the box, and then they actually built it at Langley. They built this pressurized box, and then they tested it. So the whole process was done at Langley rather than going to a contractor.
Excuse me. And that's really the what research engineers do. You do analysis, you do experiment, and we go through this, and you figure out if there are any errors, what's not correlating well.
Yeah. And that's what we did with the finite element machine too, because the computer industry wasn't really getting things practical in parallel. So we said, Dave Londorf came with the idea, let's just build one at Langley, because the hardware was getting less and less expensive. So
but this is critical now. So now you go from software, which is conducting a numerical analysis called finite element software. Now you're going into something called a finite element machine, which is it sounds to me like you're merging the hardware with the software. And talk a little bit about how you came up with this idea and what it amounted to.
Langley was such a beautiful place that Bob Fulton, who was my supervisor, he said, if something makes sense at Langley, you can do it.
Yeah.
You know? And I always had that spirit. So sometimes these electrical engineers, new Motorola 68000s, I get fascinated with those, and they'd have little courses over in the electronics division. And I told Roger Anderson, man, I think that's going to have an impact in the future. How about I attend that? And so I'd go over there and we design these microprocessors to run windmills and fans and all this stuff. And then I just dug into that. And then we decided, hey, we can build a computer just as well as the computer industry. So we got some MSI 8080s, put those together in parallel, showed that we could do it. We took the results to headquarters and said, I think we can build a big one with 32 processors. So we were the first ones that built a parallel computer. There was one that was on contract up at Illinois, but this was the first one built in-house at Langley called the finite element machine. We had to have a team of software people, team of hardware people, and applications people. Dave started out, but then he went to Los Alamos, and so I took it over, and we actually got the thing running, and that was very exciting.
And this is kind of the beauty of innovation, because you're looking at things through the lens of a structural mechanics person, solving these partial differential equations numerically. You're looking at how these calculations are being done serially. And you said, you know what, I think we could speed this up because all these all these computations could be done in parallel.
Right. Yeah, and the unusual thing then, the finite element equations, they wind up with a series, and somewhere you have to stop the series. Well, at that time, ARPANET came along, and one of my friends from Willie and Mary said, hey, we can differentiate and integrate now on the internet. So we got on the ARPANET, one of the hubs, and we're able to get these long terms and truncate them and get more accurate results than the typical finite element codes. Because somebody couldn't sit with a pencil and paper and come out with a more exacting formula for it. So we integrated that for accuracy. And we did a whole lot of things related to solving equations. We got this general purpose solver that was faster than anyone could do. We put a challenge out on the internet. Can anybody solve these 10 NASA finite element problems faster? But we get some ideas from people and insert those. But as a result, people wanted it all over the place. So that was one of the most popular software products that came out of Langley. And all of this, it wasn't all planned, which is the beauty of it. Sometimes government planning isn't the best thing in the world. Just surface up from the bottom. And our chief scientist there, Dennis Bushnell, we had something called CNI, Curiosity and Innovation or something. He said, I want you to reinvigorate NASA Langley and the research trust. So he said, choose a couple books that we can use. So I chose one that was a medical book. It said the 10 top medical innovations, and the 11th chapter was how they were done. And most of them were kind of happenstance, kind of in a research environment. And at the end, it said, well, very few, only 1 or 2 were governments funded. Some of them were just happenstance, like the first use of anesthetics and stuff was just people using some laughing gas at a chair at a party. And one guy who was a dentist or something, he came back and he had all these bruises in the morning. He wondered how they were worried, he never felt anything. And he said, that might be practical to use in dentistry. So it started in dentistry, and then some of the doctors started to use it too.
But really, that was the beauty of NASA back in the day. We had a lot of freedom.
Yeah.
We worked with people from multiple different disciplines, but it was also what some people call applied research, or what is the other word for it? But it's an applied research, use-oriented research from is another term for it. But you always have in the front of the back of your mind ideas for an application, a problem that needs to be solved.
Yes, and sometimes many of them, and you can solve, like in acoustics. I didn't think our equation solver would be useful there, but then they started using it, and then pretty soon it speeded up all their stuff. And in radar design, some of the secret stuff that was done at Lockheed, they approached us and said, can we get your solver? They got it and speeded up their stuff. And automotive, both Detroit and Ford and GM invited me up there, and they wanted to get our solver, and they used it throughout their company. And then later I found out, if you look at the car, how smooth it is, that they said they're using our solver to get surface smoothing, so they look so nice. You never know all these applications that come out. Wow, that's amazing. And so the other influence that you had, you were also hired at the same time of our good friend Jarek Sobieski. Yeah, we had the same office together. Yeah, and he was in Norway together. You know, he was over there. He escaped from Poland and came to Norway, and then brought his whole family.
I didn't know he made a stop. I didn't know he made the stop in Norway.
When he got his citizenship, I was the one that went there.
Oh my God, that's outstanding. Yeah. And of course, he was the father of multidisciplinary optimization. Right. Yeah. He was a brilliant, still is a brilliant, very innovative guy. And I got to work with him a little bit, and his branch was called the optimization branch. Mm-hmm. And so the minute you start solving these structures problems, static structures, dynamic structures, then you go into optimization, and the problem size goes up exponentially because you're calculating these derivatives. So you're constantly looking for a faster way to solve the equations.
Well, we worked together when we first came, shared the same office in 1229, and for many years worked together. And then before I retired, we were in the same office next to each other, 1293, I think, with the big spheres and all. We were over there. But I was going to say that Yarrick and I wrote a paper together for, it was a cover issue of, what is it, Aerospace America. And they had on the cover, compute as fast as you can think. Or compute as fast as engineers can think, or something. It was very cleverly, and he was good at putting things like that together. And there's a lot of things that we both did together in that article. So that was something where, that was just before I retired, and then he stayed on a little bit longer. And he said, Olaf, you left just at the right time because the research emphasis was going down. At Oak Ridge, it was going up.
Yeah, and you know, that's, talk about why I left. That's one of the reasons that I thought it was an opportune time for me to explore my other passion, which was actually becoming an astronaut flying in space. I saw where NASA was going, but you have some amazing achievements, right? You are the most humble guy, one of the most, and actually most.
You ask other people, they'll say.
No, most of the friends of Charlie that I rely on, and most of the people we've had on these podcasts that I know from industry or academia or NASA Langley, they're the most humble.
I loved her talk. That was great.
Eileen Collins, and I got to fly with Eileen Collins. What an amazing, amazing lady. But these people are so humble. And you really are, you're Olaf, because I didn't realize all the stuff you did. And I was like side by side in other offices working on different things. But I never knew this, that you were doing all this stuff.
I worked on this thing a little bit too.
That's exactly right.
Really speeded up the calculations.
That's right. One of the major awards you got was the first Cray GigaFLOP Award.
Yeah.
That's 1 billion operations per second, because of your amazing structural analysis that was over 54,000 degrees of freedom or more.
That's right.
For
the redesign of the shuttle tank. And
the solid rocket booster.
Yeah, solid rocket booster. And I called the guy. They said, you ought to check with the people that originally did the design. So I called the guy called Larry Kiefman down in Huntsville. And I said, when you designed it for the original tank, how many degrees of freedom, he said, did you have? He said, well, we used the UNIVAC that had a storage system. We could only get up to like 999. So they had to have less than 1,000 degrees of freedom in their models.
Yeah.
So upped it, we got 54,000, and still we could solve it in 6 seconds.
You know what's amazing? A lot of people that think about the Challenger accident, what caused the accident, what do they usually say?
Well, I've heard McDonald what he said, and I believe him. It should have been preventable, and if I have the feeling it was the Department of Justice. After our administrator had him Jim Beggs had him step aside. Dick Snyder's wife was in the headquarters building, and when he had to go and defend himself, he was, there was nothing to it. But then he had to step aside at that time, and then William Graham, who was a computer guy, they put him in, and he didn't know how to. He wasn't, ready for the job, and just at that time, and the president wanted it to go, so Jim Beggs wouldn't have let it happen. The real reason why we had that failure wasn't the O-ring, it was the joint. And NASA Langley did all the high-level nonlinear structural mechanics to understand how that joint actually behaved during loading. And it didn't close, it actually opened. Yes. Yeah. And so you look at, they were only using 1,000 degrees of freedom, a finite element model. How could they possibly get down to the detail you need? That's right. To understand what's happening at that joint level. And Ed's podcast talked about that, which was very good. Yeah. I think that's his, right? Where he talked about it. I don't know if Ed talked about this SRB. He actually talked about the impact problem that they were trying to solve. Yeah. But that's what's amazing about NASA Langley. I mean, we had these amazing people there that I just heard the lecture that we had at the
that Mark Lewis did on hypersonics,
Oh, yeah.
the new head of hypersonics at the Purdue Advanced Research Institute. He's now the CEO, president. And Mark Lewis said very early on, one of those hypersonic vehicles that we tested not too long ago failed because the people thought they could do the entire design analytically using CFD and not a wind tunnel. And a person at Langley told them, no, there was going to be a problem. They didn't listen to him. There was a problem. And so we go through these cycles. I remember during the aerospace plane program, we had that same issue. Some young folks thought that we don't need wind tunnels anymore.
Yeah.
We don't need hypersonic wind tunnels, even though the Chinese are building these hypersonic, we could do it all using CFD. And it's not the case, right?
Yeah.
So that's interesting. You learned that very early on, and you were out there testing. Just like that, they drum that into us. You know, you go out there, you prove, you got to validate your results by
But
multiple.
I learned from other people. Jim Robinson, he is first class. And
Yeah.
I worked with him on different things. And he was the type of guy that if he was right, he'd go to the director, you know, and he taught me that, you know, what's right is what counts. It isn't, you know, politics or something like that. And
Yeah, he was also an ex-New Yorker, so he didn't have any problem speaking up.
Bob Fulton, my boss, when I first came there, he told me several things. Two of them I remember. One of them was, he said, I'm going to be like a mother hen. I'm going to protect you from all this stuff above you so you can do your research. And another thing he said was, treat these organizational charts, flip them upside down. The engineers are at the top.
Oh,
And the
man.
other people are supporting you. The procurement people.
That is so true.
Yeah.
That
and
is
so I
so
had that
true.
impression. And so when one of the directors, his birthday was at the same time I was, so we always went in for our physical exams at the same time. And you know, I kind of felt sorry for the directors people. One time they put me over there to do some things, and they don't have you know, they come to the morning and suddenly they have all these things they plan out a day, but then they can't do what they're doing because all of these fires they have to put out.
You want to know something? The worst day of my life probably was when Mike Griffin, the administrator, said, Charlie, I want you to be director of engineering. Because my love was engineering at the grassroots level, research down at the bottom, and my whole day was filled with going to meaningless meetings.
Right.
Meaningless meetings. And my wife at the time could tell when I drove in the driveway coming back from work, if I had the opportunity to actually be in a lab with real engineers, or if I spent my day wasting at meetings.
I think Feynman, when he came for the review of the Challenger, he was the same way. They wanted to escort everybody around together to the different centers. He said, I'm just going to go and talk to the engineers myself directly.
But you said it, and actually Schultz, one of the historians that wrote Engineer in Charge, right?
Yeah,
and Crafting Flight, he basically said that was Langley's real claim to fame, that research culture, which had the deference to the people with the knowledge, no matter what their status was in the strata of the organization. If it was the lowest man or woman in the organization that had the knowledge, people listened to that person.
And that's why the publications were so important. The Langley publication, if something came out of Langley, it had to be like the word of God almost. And I think I was on one of your editorial committees, and I hope I treated you well, but I know that the paper that came out was first class.
I talk about, in several episodes, we talk about the Langley editorial process. It was butting heads, 4 or 5 people clashing, going over every little detail that you did, sometimes going over your analysis, doing something, making recommendations. It was a very, very humbling experience. And then you flash forward to when I'm thinking about becoming an astronaut, and I get interviewed. Well, actually, I was in a bar and I meet George Abbey, and he's questioning me, knowing me that I'm going to be coming up for an interview in the astronaut office. And he's asking me, well, when are you going to leave that library
Oh, yeah,
and do some real work. He considered Langley a library, and those people
Yeah.
are just playing in the sandbox over there.
yeah.
But that showed the difference, and really, I believe it's a lot of reasons why the accidents happen. Nobody connected with real researchers that could have helped them solve
Yeah.
those problems.
Remember that little thing I sent you from Pete Peterson? He sent it to Abby about our computations and how they reduce things. And you wonder sometimes if the people in the shuttle office connect with that. But I know Pete Peterson sent our stuff over to them, and whether they appreciate it or not, that's up to them.
JSC, Johnson Space Center, lost that research DNA that they had in 1958 with the 50 people from the Space Task Group. They basically lost it. And so you had this amazing career, and God, we could go over some of your amazing awards.
Well, I just say I'm sorry that I left.
FPGA, high performance computing. You did amazing things with FPGAs, right? You
Yeah,
want to
that
talk?
was a whole new way to develop computers without CPUs, which was really exciting. You get a blank piece of paper and design it. And all these people that were electrical engineers supposed to know all this stuff. You know, I was never intimidated. My son was an electrical engineer, went to Caltech, and now he's a fabulous guy. But I was never intimidated by anybody, whether they went to MIT or what, I just had the feeling that if something made sense, you could figure it out.
And we were given the opportunity to do that. And so we had great mentors that we would learn from. One of the reasons why I went there was because it was so easy to go away for your PhD, which is not the case anymore.
Oh,
right?
They paid for yours, huh?
Yeah. Oh, yeah. They pay.
Work and pay myself and pay off the citizenships.
No, exactly. I came straight with a bachelor's. I went for my master's and my PhD, and the government. That was a very amazing perk that we had.
Great thing. Yeah. I kind of felt, but in addition to that, they gave you those towards your years of service. So if somebody like me came in and paid for their PhD ahead of time, and that started, we'd be like 3-4 years behind those that were on the payroll, basically, of Langley.
And a lot of people talk to me because, a lot of my friends were going to industry when I decided to go into the government. And of course, they were getting more money. But I mean, our environment and what we were able to do, and just like you said, if you could think of something, you could do it. If you had that, it was such a free and open environment. And I really think you need that for innovation. You need that for research. You have to be able to try things, fail. The other thing that was amazing was the mentorship. And you were an amazing mentor to several people. You received fantastic mentorship. Talk a little bit about what it takes to mentor someone to actually do research.
Oh, gee, I worked with, Jonathan Ransom, because oftentimes, that was part of the culture, I think, that you wanted to pass along things to the next generation. So I worked with people at Langley and also students. They had the governor's school there, which would be the top students in the 14 schools in our area. And I'd always have a couple of those maybe every year. And I'd assign them to do things on the finite element machine, or even the field-programmable hypercomputer that we had. And those students, they didn't have any innovations. They get in there and they do things. And, typical engineers might say, oh, you can't do that, you can't do that. But these students would do it. And Jonathan, I think I started him on an Atari computer to do some equations for beam bending and stuff like that. So he got the actual idea with this hardware, the software, how to do it. And now he's the structures engineer, chief structures engineer at Langley or something. Right,
yeah, he could.
You call it right under the director. Yeah.
Is he the research director of research? Yeah.
I mean, it's pretty amazing.
But you mentored many more people, and it's a process. It wasn't just the first couple of years. We had these folks that were amazing people side by side, helping to mentor us as we're learning the craft of research.
And it's sometimes not only mentoring, but it goes in both ways.
That's right.
You can work with somebody that's in electronics on a joint program, and then you can learn from them and they can learn from you. I put in a proposal for this FPGA-based space computer. And I didn't want to do it because I had plenty of funding. I didn't have any problem with funding ever. But then Charlie Blankenship, our director, came in and said, "Oh, if that stuff sounds really good, I think you could just put in a proposal and get a bunch of it for Langley. And think about, doing that." So, it takes time to write a proposal. Well, okay, I'll write a proposal. And so I wrote this proposal. And but when I write a proposal, I always want to check what's been done before. So I checked some other stuff, and there was a guy over in electronics that Hodgson was his name, and he'd done some things like that. So just to check, I called him up and said, "I'm putting in a proposal." He said, "Well, I'm putting one in too." And it was kind of somewhat similar. And so I said, "Well, why don't I write mine and reference you? You write yours and reference me, and see what happens at headquarters." Well, the result was they liked both of them. So it was like $25 million. And they said, "We suggest that Olaf, you work closely with Bob Hodgson, and then he worked closely with me," which is what we kind of plan to do anyway.
Now, was Bob the fellow from Goddard Space Flight Center?
Who was?
Was Bob the fellow from Goddard Space Flight?
No. Bob Hodgson.
Was at Langley?
Yeah, he was at Langley, but in electronics.
Okay.
Yeah, so they actually assigned me over there. I had an office in both structures and electronics, so I worked together with them. But then he took it over the project when I was offered the position at Oak Ridge. Which I kind of feel sorry for, because a lot of my friends then and other centers, they saw I was going, and they saw that maybe they can grab the money, and they were able to get some of the money.
But
it's really feverish between the different centers. Same like Department of Energy, there's competitors among the different organizations.
Let's talk about that applied research and how usually in aeronautics and we were leading the field. We were taking our applied research in aeronautics when we were NACA, and it was advancing our industry in the United States. Also, what you were doing in high-speed computing was drastically affecting how the high-speed computing world in the commercial sector in the United States. Talk a little bit about that.
The design of the Intel chips, even. When parallel computing came along, Intel recognized that, and the other companies, and they had, like meetings that would go on that I'd often go to. And then Intel itself decided to have an Intel supercomputer users group. And of course, I was one of the main users. So we'd have meetings all the time. They put us on their board. I was on the board. They talk us about what's coming down the stream with Intel in the future. And at one time they said, we had a problem with one of our chips. Remember, one of their Pentium chips had a problem. So they said, "We don't want that again. So we're going to give a development system to somebody somewhere." So I put in for that, and I got it at Langley. And I told Jonathan, he was my supervisor, I said, "I put in for this and I get a whole development system. What should I do? Should I just play with it at home, or should I have it at work?" He said, "Do whatever you want, And so I got it at Langley, and it was the first one of a type, like 6 months access before an Intel chip. And we started doing our structure stuff on that, and we found out it was wonderful performance until it got to a certain level, and then it peaked out. So we were, one of the things for getting it is to peak back. So we told them that, and it turned out it wasn't their chip, but it was a companion chip that was managing the memory that was messed up. So we saved Intel a lot there because they redesigned their companion chip, and then when it was released, the whole thing worked. But when it was at Langley, people heard about it, and CFD people. So I opened it up so other people could do things around Langley and use that advanced chip. So we were on the cutting edge of not only structures, but on
but you were also helping industry out. You found a problem with that chip. And when you saw that problem, what went through your mind? When you saw that it peaked out, what went through your mind? What was the thought process?
Well, I kind of thought we could use it for this first part, but if we get to solving large structures problems, that's going to be dead in the water. And I fed back to them and said, to be practical, that had to happen. We also, Apple, when they came to us, they had their Lisa machine. And it was in our building, 1229 at that time where I was. They had the Lisa, it was like a big thing. I just made a comment during the break. I said, you know, can you just print this out or do something like this? They had a whole bunch of problems doing that. And then I asked them a few other, they couldn't do it. That Lisa machine never saw the light of day. And, you know, so we had feedback to Apple, feedback to Intel, feedback to the aerospace. I was out at Boeing for a whole summer to work with Turner and Bob or Miller, what's his name, Ralph Miller. And, you know, Turner was the one that had the book on finite element technology. And that was great. And then that was at the time of the SST. So I was working with two people that were designing for Flutter out there. So I really had good experience with Bartlett was his name. There was and Lalonde, a French guy and a British guy. And I was in the middle of those two designing this thing. But it was a good experience to be in the environment.
And you were doing all this cutting edge work. You were getting all these phenomenal job offers in all these other companies, but you chose to stay at NASA Langley.
And you know why? Because Bob Fulton, that was the third thing he said. He said, you're going to be getting offers all over. However, would you rather be in the point of contact where everybody's coming to be funded and you're the one that's helping to guide the way how to fund them? Or do you want to be on the other end where you're writing proposals? So he said, you get the best of both worlds if you're at Langley, because you can work in research alongside with companies. So on iPad, we developed a database system of all things. You know, who would think Langley would develop a...
I remember that. Like, why is NASA Langley working on a relational database system? You and Lowendoff and Charlie Blackburn.
It turned out that for managing all these things in the aerospace industry, you wanted to have information there, right, ready all the time. And the typical databases in banks, you had these columns of this, that, here's, you know, they just didn't fit a database system. So we came up with a relational database system with a guy at Boeing, who's now a multimillionaire. But he was at Boeing, developed it for our project. And then they had a demonstration of all the airports in the world, and you could go in and say, which one is over a mile high or something. They would come back and give them all. And, you know, and I'll tell you one thing that happened. Computer World, big magazine, came out weekly. They had a list of database systems and evaluated them on the front page. I called the editor up. I said, you've got something missing here. Langley developed this database system, and it's far and away better than any of them on your front page of your Computer World. He couldn't believe it. And so I said, he said, can we do a feature story of that? And I was thinking, well, that's getting above my pay grade, because that'll be all over the world, right? So I said, just a minute, I'll get my supervisor in the next office. And Bob Fulton started to talk to this guy. Next week, they had a front page edition about the relational information database system, using it on the shuttle tiles and all that. We were astounded by all the people. Tower, who was the head of a committee, you know, whatever appropriations, that he called up and said, one of my people in Texas isn't getting his database system. Can you guys give it to him? You know, and we had to get money down from headquarters just to get the database system out there so people could get access to it. It was phenomenal. But I think it was just because I happened to call up that editor, you know,
but
and then they wanted to do a feature story, and then everybody wanted a relational database.
And you eventually decided when a good time was for you to leave, and you went to Oak Ridge National Labs.
Yeah,
what an awesome place.
Sad for, you know, when you do things like that. I have two engineers that are sons, one mechanical, one electrical, and I called them up and I said, I'm planning to leave. What do you think? And they said, stick with Langley. It's been your whole bread and butter the whole time and all this. And I felt that way. But on the other hand, at Oak Ridge, it was really ramping up in the computer area, and I was getting all excited about that. By the way, I wear this because my first allegiance is to Langley. This is 100 years.
That's right.
And
that's right.
When I give tours at Oak Ridge, I wear my hat, and you know. So then when I talk to the high school kids, I say, you know,
but you make a very good point, though, right? I mean, NASA Langley, when people think about NASA, they think about aircraft, spacecraft.
Yeah.
And here you are, a computer scientist, and unfortunately,
I'm an engineer, I consider.
you're an engineer, but you had to become this expert in computer science and software. So you had this dual, that blending of these two very technical disciplines.
And physics too. I was a physics major. I remember one time I took my passport. They give you these diplomatic passports, and it had on it engineer. No, it had scientist. I think I just tried to do that. And then I went to the Oslo airport. They said, "What kind of scientist are you?" I said, "Well, take your choice: computer, or
physics,
engineer, or physicist, or whatever." I don't like to be put in a box. I never did.
But that's amazing though. So you went to Oak Ridge National Labs, and I'm sure you must have had a top secret clearance, right?
Oh yeah. That's stuff that we did with the nuclear codes. I can't talk about that. And I was, I guess, the only one that had access to the codes. And I don't want to say too much about it, but publications I did, I couldn't even list the title of the publication, or I'd be in trouble.
But it was you were always looking at advanced computational solvers, equation solvers, high performance computing
and supercomputing, fitting these nuclear codes. But that was just an aside. Most of my work there was related to the advanced supercomputers. And we worked 5 years ahead of where they're going. We worked with the companies. I worked with Cray a lot. We had an FPGA computer. Then there were other companies, Silicon Graphics, that worked with different architectures, graphics processors, cell processors. And so that's still going on. And it's a beautiful way to work. And when I went out there to Oak Ridge, it was like the drop in age was like 10 years. My boss was younger than me. All these people were so excited about computers. At Langley, it was like engineers were first, computers were kind of a support.
Exactly. That's what I was.
I was an engineer at Langley, so I kind of wore my engineer hat, and then the computing went along with it. And so then,
But you probably didn't get the appreciation that you should have gotten.
I mean, different. I don't worry about that because I enjoyed everything.
Exactly.
I enjoyed the freedom at Langley, and it's at Oak Ridge. It was really, what they did. I think I showed you all the places that they wanted me to go. Turned out they give you, if you give talks at international meetings, that's considered very high. So when you do ratings of people, you go to international meetings. So I ended up giving all kinds of international meetings and talks, and that was, just kind of the reward system there. Whereas at Langley, it wasn't quite the same. They didn't even at Langley want me to go to give talks at computer. What do you call it? Every year there's the computer show. Not computer world, but supercomputing. Supercomputing.
And so let's talk about that, because I think it's kind of the same reason why I left Langley. I saw NASA wasn't doing as much research. It wasn't as much fun. And that's kind of where we are. It's kind of sad because I kind of wonder about how are we going to be the best in the world in space, in aerospace? Are we going to be second to China? And here you are working in another field where we're very highly competitive with China.
We're number one now.
And that's what I want to hear. And I'm very glad to hear that from you.
Well, there's going to be a new list in June. But I think we'll still be number one there. But
okay. And so
every 6 months, there's a top 500 that's issued around the world of the top computers. So June and November, it's, so June is coming up, but
it makes me feel good that, all right, NASA's not doing this research, but who is? And what you're saying is the Department of Defense, the Department of Energy is putting enough money into doing basic and fundamental and applied research.
Yes, the Department of Energy has a good strategy with that. I'll tell you a little side story. When I was at Oak Ridge, I was in my office doing my research. This guy that has been there a long time called me up, and L. Geist, and he said, "Olaf, I want you to come to my office." I didn't usually go to his office. He was doing all this neat stuff everybody loved. And he shut the door and he said, "Olaf, I want you to apply for this position in DOE headquarters. I said, why would I want to go up to headquarters? When you're at Langley, that's one of the things you didn't want to do.
Exactly.
Said, oh, but it would mean so much for Oak Ridge. If you could be there, you'd know what was happening and all this. And this person was leaving. Oh, so I said, okay, I'll apply. I applied and they selected me and they called and then I started to get serious. I said, what's my salary going to be? They said, oh, you're going to have to go back to your salary at or the same as a government employee. Well, I was already had my retirement from NASA plus this. It would be like taking about half of my salary if I had to take that position at headquarters. So I had to turn them down, but that was unfortunate.
And so that makes me feel good that in high-speed computing, so you think the way you were watching people mentor new scientists and researchers at Oak Ridge National Lab, you think that's the way NASA used to do it at Langley? They're doing a good job?
Yes, very much involved with the customer, so to speak. Like at Langley, we worked with Boeing and Lockheed and McDonnell, and we used to go back and forth. We had a NASA one plane, you may remember, that came to headquarters. Yeah. And we flew up here to Minnesota to some of the computer companies up here and fly to McDonnell up to Bethpage, New York and all. So we involved all these, and that's what's being done at DOE. They have meetings with all of the customers around. I mean,
but the environment itself for a young person starting up, getting the mentorship, like you were able to mentor people like Jonathan Ranson and other folks. Yes, you see that level of mentorship and they really take up, they really put it at a premium. It's very important.
Like when I do the tours, we go around to different sites, whether it's the high flux reactor or the SNS, which is the spallation neutron source, or the biology, or it's really the main research center in the country. And it's open research. Most of the research that is done on the supercomputers, not for people here at Oak Ridge, but it's other people. So we have a whole group at Oak Ridge that supports it and they work with the others. For example, Pixar Films, they didn't have a supercomputer. They wanted to try and see if they could get some of their films so they'd work better and more accurate. So they got time on our supercomputer to do that. And some of the people from Langley came up to visit me and I took them by, and then they started to get time on Oak Ridge Super. So these are open supercomputers. You just put in a proposal, and I was on the committee that selected people, and it's a very open saying that Congress wanted to have a center like Oak Ridge where the industry could use it. And the advantage is we got all the people and knowledge. So now we got an Air Force computer here too, a NOAA computer. And there's another one, I forget what agency that is, but there's other supercomputers housed at Oak Ridge. Well, of course, NSA, right? I'm not supposed to say that. But anyway, we have the center of not just for Department of Energy, but the other computers that are situated.
Wow. So this was
when they put in a proposal, they say, well, we've got all this infrastructure already there. Nobody can compete with it.
So really, to answer back to your sons, this was the place for you, Olaf. Yeah, I mean, this was really where you should have gone, and you did. And
remember that one chart. And by the way, any charts that I've had in the background preparing this are on my website, olaftn.com.
And that's right.
Charlie's picture, click on that, and you can see some of the background. But one of those charts showed that every 10 years, the computer technology was 1,000 times faster. And it goes back to when I got the GigaFLOP Award, and that's been many cycles since. So that is a technology that I don't know what's more rapid than that. And it's still continuing to go up. At first it was the processors, and then it started to get parallel, and then it started to use FPGAs and GPUs and other things. So it's a technology that affects all of us, and now it's artificial intelligence.
This makes me feel very comfortable that in high-speed computing, we're neck and neck or leading in the world. That makes me feel very good. The other areas that I'm a little bit worried about, and I'd love to get Mark Lewis, who's now the CEO of the Purdue Advanced Research Institute in hypersonics, to pulse him and see how we're a little bit behind in hypersonics. What
Like
about, yeah, and that's a big deal because, you know,
we
they
had the X-43 at Langley that worked, and it was, and then the X-51 the Air Force had. So we've got 2 successes.
that's right. And what was I gonna say? Yeah, so we're 5 years behind the Chinese, and they're killing us in education because they're putting so many students out there and in building resources, and we're trying to catch up. But the other area that you would know something about that I'm a little bit worried about, besides artificial intelligence, is cybersecurity. It seems like we are constantly being hacked by the Russians and the Chinese. And so how do we stack up cybersecurity wise? It seems like we can't keep anything.
Well, we had an attack at Oak Ridge, and it came in, well, when I was there, it came in through a Microsoft. You know, somebody had sent an email message that said, and of course, everybody's interested. It said, our retirement system rewards are, you know, something about that. And everybody wants to find out more, right? But we're trained never to open anything. Well, I guess a couple people opened this, and then this came in through a Microsoft. But it didn't affect our supercomputers because those are all connected through a different network, and it's mostly Unix. There's not much Microsoft. So it entered that way. However, I'll give you another nugget. I give the tour groups, and we get experts that come and, you know, we can ask questions to. And they have a whole cybersecurity group at Oak Ridge. And some of the students, they were, you know, really into computers, and some of them hacked things themselves. And there was a girl and a guy, and both they weren't worried, and they said, is there any future for people like us that love to hack at Oak Ridge? And they said, as a matter of fact, there is, that we're hiring people to prevent, you know, so they said, you know, there are careers for that at Oak Ridge to counter hacking.
Yeah,
I think they do a pretty good, from the people that I saw, they do a pretty good job, but you never can tell. And it's always the weakest link too. If you have a computer system and the network and all that, someone along there, you know, we use the Dobbs and all these kind of things, but
hey, I'm gonna ask a wrap-up question. And this is going to be like one of the final questions. I could talk with you for days, and I'm glad we reconnected, Olaf, because I'm going to be pinging you a lot more. But one of the questions I want to ask now, because we both love NASA. I mean, I had a 45 plus year career there, you 30 plus at least. 35. And so I don't like where we are now at NASA. I'm kind of wondering why we even need it. What do you see that you could say is possibly where NASA has gone astray, and what can we do to get us back to where we used to be?
Well, of course, I haven't been there since 2005, so people that are there know better, but I've been working with people there, and I noticed there's probably a lot more contract management at Langley than there used to be. That's what Yarrick said anyway. He said, I left at the right time, that a lot of were burdens. You have to manage these contracts rather than do the research yourself. And I think that is really not good. I guess from one standpoint, we're depending on industry to come up with things, and everybody's thinking that's a lot cheaper. And maybe, so I don't know that there's one way that's better than the other, but there has to be the research, or else there's going to be problems.
Yeah.
And so you have to have some nugget of research somewhere that people can bounce off and get their ideas. And if you have a company, they're all enthralled in their own security of stuff. So nobody's going to look at it, even if they have a problem, right? So, and they're not going to admit to the problem until they have a failure. So I like the idea of maybe an open environment, of a research environment. People can bounce things off. Maybe it can help secrets to the companies, and they do that at Oak Ridge. They allow people on our supercomputers from companies, and not allowing other people to access their results if they pay for their supercomputer time.
Yeah.
But others can just put proposals and then get the supercomputer time free if they promise to publish everything. So that's the market, and that's what they do at SNS too. They have people get beam time up there for free if they have a great idea, but commercial interests, they have to actually pay for the beam time. Where are the countries? Japan, Canada, Germany, they pay for time on the Oak Ridge SNS system.
Yeah.
So I don't have an answer to that. There must be some people that I think you've had more experience at NASA. You can see the whole thing. But
Yeah,
I really love the environment we had, and I wish it would continue. And I think I would have been able to stay and continue that way because I had plenty of funding. We had that 25 million. And but Dennis Bushdell, you ought to get him on. He was the chief scientist for many years. He still may be there. I don't know.
I think he is. I think he's still the chief
because he was
scientist.
saying, what's happened with quantum computers? And he always, I remember one time he said, oh, I don't know if we should fund this particular stuff because quantum computers are right around the corner. I said, who tells you that? Well, I'm reading about it and all that.
Yeah.
And he said, well, I'll fund you if you can write me a white paper that says that quantum computers won't be here within the next 5 years or something. So I contacted my friends at NSA, people at Los Alamos and others working on company. And I said, this is only going to go in a white paper to Dennis Bushdell, so don't worry about what you say. And they all said, oh no, it's not going to be 10 or 15 years still. It's still like 10 years away. And that was back like 20 years ago. So
It's kind of like fusion.
yeah, it was like a flash in the pan. And maybe it's getting closer, but who knows?
Hey, I just want to say thank you so much for spending some time. I'd love to
appreciate it.
I'd love to have you back. I'm definitely going to be calling you up for some other ideas that and questions I might have because you're the guy. And I just want to thank you so much, Olaf. It was a pleasure to have you at NASA Langley, and I'm sure they appreciated you at ORNL.
And you used to work out by the golf course, right?
That's right. That's right.
The editorial committee. Oh, there's the golf course right there.
That's right. And I used to look out. It's a little different color. I used to look out. I used to look out the window and I used to watch the F-14s, F-15s taking off, F-15s taking off. And I used to go, boy, I would love to fly.
And you had a big tower there too for the thermal structures, right?
Yeah, we had the 8-foot high temperature structures tunnel, one of the few hypersonics tunnels where you could actually test the entire scramjet engine inside the tunnel.
Yeah, and great people. The people are everything.
That's right.
Yeah,
That's
Jim
right.
Robinson, I have high respect for him. And Jim Starnes.
Yeah.
Bolton. There's
amazing people. We were very lucky. I want to thank you, my friend. You have fun in beautiful Tennessee.
Well, I'm in Minnesota now visiting my mom, who's 103.
Wow. That's amazing. Good for you.
She's got all her Norwegian stuff here. This is welcome to our home.
All right. That's amazing.
Yeah, well, she's going to be 104 pretty soon. So.
Well, that's great. Great genes, buddy.
That's right. There's an APOE test, I told, and I got her gene, they said, and one from my dad, and he was over 90. So
all right.
Hopefully I'll be here for a while.
Excellent. You take care, Olaf.
Okay, thank you very much. And
thank you, buddy.
Can't say enough good about you, Charlie.
We hope you enjoyed this conversation. If you learned something new and this story made you think, then share ITSP Magazine with your friends, family, and colleagues. If you represent a company and wish to associate your brand with our conversations, sponsor one or more of our columns. We hope you will come back for more stories and follow us on our journey. You can always find us at the intersection of technology, cybersecurity, and society.